All right. So it took me a little while to decide exactly how I wanted to approach this topic. The textbook, the Physics for Scientists and Engineers by Randall Knight, he hints at parametric equations and then moves on. Since you all have actually had calculus, so you could take this section of Physics 1, I have decided that I would like to talk about parametric equations just a little bit more than what the book does. So this topic is a little bit more advanced than what you might see in a Physics 1 course. But parametric equations are really fun to think about and talk about, and I enjoyed it. So I thought I would include just a little bit more than what you might see in a typical physics course. Later on in your junior, senior level engineering courses, if you take like a engineering dynamics course, you'll probably see this come up again. If you take Calc 3, you'll definitely see this come up again in Calc 3. So I don't want you to think that it's not needed. It's just think about it as like you're getting to see just a little bit ahead of what you might be doing in an engineering course or a junior senior level physics course. So for those of you that are moving in that direction, this will be very much a preview for what you'll see in the future. Oops. All right, so let's quickly review velocity and graphically calculating velocity. So as an object moves, its velocity vector, remember that velocity is a vector. Its velocity vector can change in two ways. Okay, so you can have a change in magnitude. So that's a change in speed, speeding up, slowing down, right? So the magnitude is your speed. You can also change the direction of the velocity vector. Okay, so maybe you're going at the same speed, 5 miles per hour, but then you turn, you're still going 5 miles per hour, but that turn itself is also a change in velocity. So we have the direction can also change, which obviously indicates a change in direction. Okay, now these changes, they manifest as an acceleration. So anytime when we see an acceleration or see speeding up, slowing down, change in direction, that's all the same thing. These changes are, that's how we know that these changes are happening, is because there's an acceleration. Now let's think about how we actually calculate that acceleration and the acceleration vector. So let's say we have to find the acceleration between some velocity n and then some velocity at a later time. Okay, so we have some particle that's moving from position 1 to position 2 to position 3. Okay, so as it does that, we've got 3 different positions, 2 different changes in velocity here. So it's got one velocity in the first step, 1 to 2, and then another velocity in the second step, 2 to 3. Clearly, the velocity is changing because we're changing direction. It's moving more to its left. So let's remember how we do this. We have to calculate the difference between the final velocity and the initial velocity, or v2 minus v1. It may not be the final or the initial, but it's at least for this little like 3 position problem, for us it'll be the final and the initial. So our acceleration is going to be, and this is going to be written very simply. This is going to be simply v2 minus v1. Now remember, when we do this, we have to flip v1 because we're subtracting, okay? So v2, nothing happens there. Okay, well, that's just our step at a later time. Okay, so this is essentially just v2. All right, so that stays the same. We have v2, nothing changes. It just gets moved down. Now here's where we flip. Okay, you can see what's going on. It's drawn in this third panel, but I can draw it here as well. It's going to point the exact opposite direction from where it started. Okay, so we're just flipping it and using the tip to tail method. Okay, now we just draw in that difference. Okay, so once you draw that difference in, that is your that's your change in velocity, your delta v. And this is also the direction of the acceleration. Okay, so your acceleration is proportional to your change in velocity, but we already knew that. That should be a review for us. Now we can actually jump back to the original problem. Once we did our vector subtraction, we're subtracting the first one off, v2 minus v1, the original. Okay. Once we do that subtraction, we get the direction. We can just draw in the acceleration vector. So even though we have this sort of curved motion going on here, our acceleration vector is actually pointing inward, sort of toward the thing that we're curving around, so to speak, is pointing into the curve. Okay, and of course, this is the average acceleration at that midpoint. Okay, so your acceleration vector will always kind of be in between where your velocity is changing. Okay, now let's think about this acceleration vector a little bit more. So in a Cartesian grid, okay, we've talked about that. That's just your x and your y coordinates. Now in a Cartesian grid, an acceleration vector can be decomposed into two components, just like any vector. Except here, instead of just doing like an x component and a y component, we're going to talk about it in terms of a parallel and perpendicular component. And this is parallel perpendicular to the direction of motion. All right, so if you have a parallel piece, so if it's pointing in the same direction as the motion, that means that's the piece that's in charge of changing the speed, so to speak. So that's our double lines here. You might remember from high school geometry, the double lines side by side like that means that it's parallel. So the parallel part, well, that changes the speed of the object. Okay, now we have, instead of the part pointing with the direction of motion, we have the part that points perpendicular to the direction of motion, and that's what this little upside down T means. That's just perpendicular. So this perpendicular piece, that changes the direction. So each component of your acceleration vector is responsible for something. It's either a part that's changing your speed or a part that's changing your direction. So let's look at this example here, the ball rolling down a little hill here. Okay, so you'll notice as the ball starts, the velocity, because it's got to accelerate downhill, we're releasing it from rest, so it's got to accelerate downhill. The velocity is slowly getting bigger, right? You'll notice that these velocity vectors, they keep getting longer the longer this ball rolls downhill. And all that's showing is just that it's speeding up. So that means, okay, well, we're speeding up going down the hill. The parallel part, okay, so this is going to be the parallel part. The parallel part of the acceleration vector is pointing in the same direction as the motion. There's no perpendicular piece, right now. All right, there's no, that should say 0 meters per second squared if you can't read it. But essentially the vector, all of it is pointing parallel, and it is responsible for increasing that speed with each step. Now, notice as we start turning in the valley here, start going up the other side, when we get to the bottom, that's when we sort of keep the same speed going into this valley as we do coming out. So the only acceleration is literally just that change for just this one step. Since our speed's the same, you'll notice the vectors on the left and the right are the same length. So for this one step, the only piece of the acceleration is actually perpendicular. The only acceleration that we're getting is a change in direction. So this here is our perpendicular piece, and also down here, we have no speeding up or slowing down. All right, and you can check yourself if you'd like. Um, all these extra circles here just show the vector subtraction that we've done in the previous slide. This is just a couple of examples. It lets you at least get to see some more delta v's here, so you can see where those acceleration vectors are coming from. Now, here's another important point. Notice as we go up the hill, well, obviously this ball is going to slow down. So you'll notice we've got this, I'm going to call it a positive v, and we also have a positive displacement, and I'm just going to simplify it with x. So you'll notice that even though we're moving to the right, we have a positive velocity and a positive distance, our acceleration vector is still negative. Okay, so the acceleration vector does not have to point in the same direction as the motion. What this is telling us is, since velocity is pointing to the right, but acceleration is pointing to the left, what this is saying is that those velocity vectors are getting shorter and we're essentially decelerating. Okay, this is a negative acceleration that's slowing us down. So of course, a negative acceleration will point in the opposite direction of motion. So we'll say negative. And I'm saying negative in quotation marks because sometimes you can imagine if this ball were left alone, it would go up and then start coming back down the hill again. So just in this one specific instance, this acceleration for now is slowing the ball down. If we let it go, it's going to roll down the right-hand side of the valley and speed up again. So that quote-unquote negative acceleration would then become the accelerating factor here to speed the ball back up. So negative excel. Ooh, you know what? I'm going to abbreviate and make our lives a little easier. So negative acceleration may point opposite to the motion when an object slows down. All right. So here's a special case of that, centripetal acceleration. So the whole idea here is that centripetal, here's a point that I do need to make. So centripetal and centrifugal forces are completely different. You'll notice I've marked out accelerations here because even though we are talking about centripetal and centrifugal accelerations, these come from forces. This will make sense a few lectures from now. So that is just a little hint as to what's to come. We'll talk about these forces later on, but for right now, we're going to talk about them as accelerations. So centrifugal forces, centrifugal accelerations aren't real. That's something completely different. Right now we're talking about centripetal, with a T, centripetal accelerations. And what these do, these always point toward the center of a circle. So this acceleration that always points toward the center of a circle. And this is our centripetal acceleration. So two examples, and we can actually use the same picture for both. So if you're accelerating on a Ferris wheel, which is usually once the Ferris wheel gets started, is a constant speed, right? So the velocity vectors are all the same length. So I'm going to say V are all the same. Okay, so you can imagine if we take this figure that we have here and we turn it up vertically, well, that would be our velocity vectors as we ride the Ferris wheel. And you'll notice that since the lengths are all the same and we try making the same turn every time, our acceleration vector will always point toward the center. Okay, and you can see that up here if you need to convince yourself. So you'll notice that our second step, V2, which is Vn plus 1, minus Vn, okay? So we're just going to take these two vectors. Here's V2, here's V1. Ooh, I'm going to see if I can change my color again. Yeah, much better. We'll highlight them with a brighter green. So there's my V, my second step, okay? So that comes first. Then I subtract my first step. Okay, so that means I'm going to flip it. So you'll notice that it's been flipped 180 degrees. So when I take these two vectors I've highlighted in bright green, okay, and I find that difference, remember that difference using the TEL method, that's going to be my new acceleration, which is right here. Okay, so that acceleration, that delta V, is the same as this inward-seeking acceleration. And if you need to convince yourself, you can like go through and maybe do one or two of these around the circle. But what you'll find is, since the velocity vectors are the same length on each side, that symmetry, when you do the vector subtraction, will always lead to the same acceleration. And it always points to the center. Okay? So that's a vertical example with a Ferris wheel. We could also just lay this down and think about just a small piece. So maybe we're thinking about this piece here. Okay, so we've got a car accelerating around a smooth curve. So you'll notice, since it's a smooth curve and the car is driving at a constant speed, okay, the only thing that's going to be happening is its direction is going to be changing. So that's actually a centripetal acceleration. That's what's keeping the car in that curve, even though it's driving at a constant speed. And the centripetal acceleration is that inward-seeking acceleration. All right, let's talk about some 2D kinematics. So let's see, I believe we've talked about this in more or less in the previous lecture about vectors, but as you may recall, the position of a particle from the origin at a particular time is given by the position vector. Okay, well, the position vector is essentially just going to scale our unit vectors. Remember the I hat and j hat? Let me make sure that's in here where I think it is. Yes, excellent. Okay, yeah, chapter 3. From the text, if you need a refresher, the text does a pretty good job of going over these. So here we have this one value, we have this x. It's not, this x here is not a vector, it's just a magnitude. It's a number that we're going to scale I hat by, okay? So you'll see over here the picture. So x is this length, and all we're doing is we're just multiplying our little unit vector, our little I hat. We're multiplying I hat by this length and essentially taking the length of 1 and scaling it up to what it needs to be. And remember, the I hat direction here, this is only showing how much of R is in the x direction. I hat does not care what's going on in the up-down direction, just the side to side. And the I hat, when it's scaled, is going to tell us how much of our position vector is actually in this direction. Same thing with y. Okay, so y is a scalar that's going to scale the j hat direction. Okay, so turns out this y magnitude is this particular length here in orange. Okay, and that's just going to scale our j hat direction. So even though this particle has this trajectory, so you can see that whatever this particle is, we don't care. We're using the point particle model. So whatever we're looking at, this object is just traveling along this trajectory. And you'll notice that what we have here, this xi and xy, this is a representation it's static in time. Okay, so this is just one moment is at position x and y. Okay, so here's our coordinates. Okay, well that's cool, but what if we want our r vector, what if we want our position vector to actually follow along the trajectory? What if we wanted a way to generalize this and say at some time t, t equals 5 minutes, t equals 5 seconds, we can plug in whatever we want to, but at some time t, we want to know what our r vector, our position vector is going to look like. All right, so this is the whole idea of like, okay, let's let R evolve over time. So the idea would be we have some distance, like some position vector. Let's make it a function so it'll actually move for us instead of just like representing these things one place at a time. All right, let me clean up that little note. All right, so the position vector x and y all change with time. So what we'll do is we'll actually represent them as a parametric equation. The idea here is that we're going to let this evolve over time. R is a function of t. And then that means our x position and our y position, these are also going to evolve over time. So now they become functions of time. So the idea here is that x of t only describes the object's movement in the x direction, okay? So in the same way, the y of t only describes the object's up-down motion, or the y direction. So all that's saying is essentially, where do I fall? So x of t is just telling me where, at some time, where do I put my coordinate? So this could be x of t1, this could be x of t3. All this is saying is that somewhere along the x-axis, I have to drop a coordinate. Okay, well, that's going to have a corresponding y-coordinate. So at some time, let's see, down here I said t3. So same thing here at y of t3. That's the same time as the x-axis. Well, that's where my position vector on the y-axis is going to be, or at least my y component of my position vector. So the idea is that these x of t and y of t's, they're not really vectors, they're just telling you how your coordinate, if you can imagine sliders, one on the x-axis and one on the y-axis, they're telling you what those sliders are doing over time. So let's take a look at this example. Notice that the trajectory, which is up here, so we have x of t and y of t. It looks kind of similar to the previous example, but I've modified it just a little bit. So let's slow down for a second and really think about what's going on. In this trajectory here in the top right, we have y. So this is the up-down direction. That's usually what we'll use the y direction as. Sometimes you could think about it as like left, right, forward, back, and you're looking down on something. But for now, we'll just say that this is your vertical. So we got maybe a roller coaster here. I don't know. We've got something going up, down into a valley, and then back out again. So we have the up-down position, and we also have the side-to-side position, or the horizontal position. Okay, so this is not over time. See, we have a position on the y-axis and a position on the x-axis. So this motion here could take 5 seconds, it could take 5 years. We don't know because there's no time axis here. We just know where the particle's been. We don't know how long it took to do it. So that being said, what we can do is actually look at how fast and where the coordinates are over time. Okay, so let's look at the x direction first. So here, what it's saying, and I'll go ahead and point out that this object went from essentially went from here to here in 2 seconds. So I'll mark that here in the bottom left. You'll see that t is from 0 to 2. I'm not going to include units because the units will make this very messy. In the future, you should include your units in all of your calculations and all of your numbers. So for this one example, This is going to be an example of do as I say, not as I do. I don't want to throw in a bunch of extra letters to complicate things because parametric equations are a little tricky. All right. So the idea here is that essentially in the horizontal direction, we only care about these first 2 seconds. So we're looking at this piece. You'll notice that this is the x piece here, that the x direction, the coordinates are speeding up, so to speak. So here at t, so this is a time axis down here. Okay, so this is x as a function of t. So at 0 seconds, our x coordinate is here. Okay, at 1 second, we're here. Okay, so at 1 second, oh, excuse me. So at 1 second, we're almost halfway to 5. So here's about 1 second, and then by the time we hit 2 seconds, we're already over here at 7. So you'll notice. So this is t equals 0, t equals 1, and then t equals 2. You'll notice that my coordinates, they're speeding up, they're spreading out. So if we want to look at t equals 3, that's going to be even further away. So the idea here is this acceleration, this horizontal acceleration, so this is a horizontal acceleration, and it's just speeding up where my x coordinate needs to be. Now, all of these x coordinates, so like, for example, here at t equals 1, all of these x coordinates, they also have a corresponding y. So let's change colors, okay? So if my x coordinates are getting really stretched out, and the higher the time value is, the further apart they're going to be, what is my y component doing? All right, now it looks like my y component here is a sinusoid, which means it's just going to go up and down and up and down. Okay, so you can see here. What's going on is it's actually oscillating around the value of 2, and we can see that over here in our plot. That checks out. And then it goes up to 3, and then down to 1, and you can also see that here in our plot. But remember, we're only interested in the first 2 seconds. So we only want from 0, 1 full cycle, from 0 up, down, and back up again. So that highlighted part there in blue, that's all we're worried about, because this particle is only traveling in the range of 0 to 2 seconds. So what you'll notice is essentially our y slider on our y-axis goes up, down, and back up again. You can see that in the plot of the trajectory. So as I plot it here, we're going up, down, and back up again. Now, the only reason that this is more stretched out than our original y plot over here is because those x pieces. Remember, the x coordinate is getting stretched out and it's accelerating. So we're essentially taking this sinusoid and then stretching it out, because the x piece, even though the y piece just oscillates, the x piece is really stretching that out, kind of like a spring. So that's the idea of like just thinking about what each x component and what's going on the x-axis versus the y-axis. That's what's going on here. We just have to break them apart, and each one we can actually represent with a function. So you'll notice here on the horizontal piece, we have a function. Over time, our x-coordinate changes just like this function here. It's a polynomial. That's where that acceleration comes from. And then likewise, our y piece, well, that's got a sinusoid, right? So there our sine function there, 2 plus the sine function, that's what's given us that oscillation. So we've got these 2 coordinates, and we could write any point on here. So like this piece here, or just in more general, all we have to do is just say that our x piece changes with time, and our y coordinate changes with time. It's just like plotting anything on an XY grid. It's just those grid points can move, and then these functions tell us how. All right, now if we look down here at our parametric equation, well, we know from talking about vectors, we have an I hat piece and a j hat piece. Well, all we have to do is just stick in our x piece, right? How does x change as a function of time? So how do we scale the I hat as a function of time? And then how do we scale j hat as a function of time? So this is telling us what each of those sliders on the x-axis and the y-axis are doing. Oh, there we go. All right. So just like with 1D kinematics, we can actually calculate a displacement vector. Yeah, I just want to make sure I didn't skip anything. All right. So you guys are familiar with the displacement vector. It's essentially just your second piece where you ended up minus where you started from. Okay, so that's going to be just R2 minus R1. Well, now these things, our R2 and R1, we're talking about very specific places. So these have a very specific time. It's not just R is a function of t. It's going to be R is this at this time. So R2 is this length at time 2. We don't know what time 2 is, but it doesn't matter. All right, so that's where we ended up. Now we have to look at where we started. So just to make sure we all remember, all I'm doing is this same equation that we've seen so many times to calculate displacement, but R2 and R1 can change with time. That's why they're functions. So we have R2 at time 2 minus where we started this movement from, R1 at time 1. Well, we know R2 is going to have an X and a Y component, right? So let's see if I can do this. I will do orange. So R2 here is going to have an X piece and it's going to have a Y piece. All right, so that's going to be the I hat and the J hat directions. And we need to know how much those are. Well, this X piece, whatever it is happening at time 2. This Y piece is also happening at time 2. All right, so that's where this is coming from. Here's our X piece for R2, and here's our Y piece and this is for R2. All right, same thing with R1. So I've got it here in green. I could draw the same thing on the right, but if you want to sketch it in your notes, that's fine. I don't want to put too many colors on these plots. Sometimes it's hard to see everything once it's all marked up. Let's see if I can do this. Perfect. Okay, so over here, this green piece, this is just R1, and this is also at a particular time, T1. So the fact that I'm using T2, T1, that means I've locked them in at a specific time. Okay, so we have our XY components of these vectors, and these vectors are being subtracted. Okay, so we have the orange minus the green. But since this is just an addition problem, essentially, addition and subtraction, we can move all these vector components around. So what we'll do is we will group all the x pieces of these vectors. Okay, so you notice I have the x piece of R2 and the x piece of R1. Okay, well, I'm still subtracting because I have to find the difference between these vectors. Okay, well, that's going to be plus. Okay, now I do the y pieces. I need to group my y2s, my y1s. So now I have all the x's and then all the y's grouped together. Notice all these things are still scaling at I hat and j hat. Well, you'll notice that a x2 minus x1 and a y2 minus y1, that's just a delta x and a delta y. So it turns out, there we go. So it turns out that the displacement vector in 2 dimensions is still just the same as like your change in your x and your change in your y. Okay, you'll notice here, same thing's going on up here in the plot. So I'll change to, I don't have a lot of colors. Let's do black. So you'll notice, essentially, my displacement vector, the vector components of my black displacement vector, well, that's just a delta y and a delta x. When we calculate those just like we did in one dimension, we just have two of them floating around, and they scale the I hat and the j hat unit vectors. Okay, so what about velocity and acceleration? Well, the good news is it works the same way. So I know this looks a little gross, but let's break it down and think about it. Okay, so if we just look at this first piece. So our velocity is essentially just the displacement over how long it took to do that displacement. But then if we take the limit and let that time get really tiny, well, that just turns into the derivative. So the velocity is just the derivative of the position over time. That's we've learned from like day one. Okay, well, when we apply that limit to r, we can distribute that through to the components. So that's exactly what's happening here. We just take that limit and apply it to the change in that x, how we're moving in the x direction, our slider on the x-axis. Well, we let those changes over time get really small. And then same thing with the up-down on the y-axis. When we slide our coordinate there up and down, we let those over time. That you can make it really small. And it turns out that's just a derivative in just the x direction and a derivative in just the y direction. So it's dx dt, dy dt. And then to make it super easy, all we have to do is just say, well, the velocity vector is just the magnitude of our velocity in the x direction. We scale the I hat vector, or the I hat unit vector by that. And then our velocity in the y direction, up down piece, we scale j hat by that. And then we've converted our position vectors in 2 dimensions to velocity vectors in 2 dimensions. So it is important to note that the instantaneous velocity vector is tangent to the trajectory. And you'll notice that over here in the plot, that instantaneous velocity vector looks like a tangent line from calc class. Now we can do the exact same thing again. You'll notice we're just doing the limit with a change in velocity over time instead of a position. Same thing happens. Second derivative of your position in the I hat direction, second derivative of your position in the j hat direction. That's your acceleration. Although the instantaneous acceleration may or may not be tangent to the trajectory. So you'll notice over here that the instantaneous acceleration is not necessarily tangent to anything in particular, which is totally fine. So let's look at an example. I'm going to use the same x and y parametric equation from that previous example, the previous plot, and we're going to answer a couple of questions about it. So consider the previous particle where the trajectory is given by this nice parametric equation. So here's my x direction and how it's changing over time. So this is just telling me how fast or slow at any given time my x slider for my x coordinate is moving horizontally. Same thing here. This is telling me where I need to slide my slider up or down to make that x component of my coordinate. Okay, and again, this is only over an interval of 2 seconds. So you'll notice the plot here, even though the plot goes from like 0 to 8 on the x-axis and 0 to 5 on the y-axis. These are still positions. So this is in meters, this is in meters. So we don't know if it took 5 days, 5 years, 5 centuries for this particle to go through this weird parabolic motion. We just know that this is where it was. The time, essentially how long it took to do that, that's nested over in the equation, not the plot. So do keep that in mind. Not all the plots we see in this course are always going to be as a function of time. So first question, um, where are the turning points of this particle? And remember, a turning point is essentially when your velocity decreases, hits zero, then goes negative, because that means you're essentially turning around. If we're running to the right, we have a positive velocity. If we stop, we have zero, and we turn around and run to the left, that's going to be a negative velocity. And that's exactly what we're talking about here. Okay, so the first question is where are the turning points, and where does the particle experience the most acceleration? So let's think about these turning points. We know that we need to figure out where the velocity is 0 meters per second. So that's going to tell us where the turning points are. It could tell us where an object is moving to the right, stopped for a second, and then kept moving to the right. That is not a turning point. That is just a place where the particle stopped. We want to know where it's going in one direction and then changes direction, goes the opposite direction. So we need to, even though there's several ways when the velocity could equal 0 for a second or multiple seconds, we want to find out when does the velocity equal 0 while the particle's changing direction. So let's think about x direction turning points. Here's what our particle is doing in the x direction over time. So you can imagine this is where our points on the x axis, they're getting stretched out because it's accelerating the x direction. So for each second, that position is parabolically further away. Well, we need to figure out where velocity equals 0, so we can take the derivative and calculate the velocity as a function of time just in the x direction. So you'll notice that there's little v sub x there. Okay, so where does this function equal 0? Well, it turns out there's only one place, and you can do the algebra to figure this out. But you see, if you plug in a negative 1/9 second in for the time, that's where you're going to get a velocity of 0. And that's the only place. Now, the problem is this time occurs outside of our range because we're only curious about 0 to 2 seconds. So there are no turning points in the x direction. Okay, so that's one direction we don't have to worry about. The y direction, that's a little more complicated. Okay, so remember, our y direction, that's where this particle is getting this weird up-down motion. As it's traveling in the positive x direction, it's also going up and down. Now this y of t here, that's what's responsible for the oscillation motion. So we need to take the derivative, okay, and you all took calculus, so you can convince yourself that this is indeed the derivative. Once we have this derivative, we have to set it equal to 0. Okay, so where does this equal 0? So it turns out there's lots of places. Remember that the trig functions like plotting cosine, plotting sine, those, well, they keep hitting 0 over and over and over because they're periodic and they oscillate. Well, we have to find the ones that we're interested in. Remember, our range is only 0 to 2 seconds. So it turns out only these first two, a half a second and then 1.5 seconds, or 3/2. At these times, those are two times that fall within our range where there may be turning points, because that's where the velocity equals 0. So the question still remains, which one of these are turning points? Okay, so to figure that out, let's think about this v of y. Okay, so here it is again, pi cosine of pi t. All right, so since the periodic function is involved, there's going to be some oscillation. I've got it plotted over here. So this is actually pi cosine of pi t. All right, now remember, we're interested in these two points. We have a half a second here, and then 1.5 seconds, or 3/2. Now here's the trick. Notice, as we're reading this plot as a function of time, remember this is just the y direction. Okay, this is just the y direction. So you'll notice we have a positive velocity. Okay, that means we're going up velocity is positive in the y direction. We're moving up toward the sky. All of a sudden here at a half second, our velocity hits 0. Okay, so we went up, and now all of a sudden we've stopped because the velocity at a half a second is 0. Okay, well now look at what happens. As soon as we get past this one little instance where we stop, well now our velocity plot is suddenly drops negative. So that means our object's turned around. We have a negative velocity. We're going down now. So that has to be a turning point. We started going up, our velocity hit 0, and then the only way to have a negative velocity now is to go back in the opposite direction. So now we're falling toward Earth. Okay, same thing over here at this second point where the velocity is 0. Well, we were falling toward Earth, right? It's negative, but then after this spot where our velocity hits 0, well, then we start going positive again, going back up into the sky, so to speak. So because we have essentially a change of sign around our 0 point, a change of sign indicates a turning point. So these 2 points at a half a second and 1.5 seconds, these are actually both turning points. So where are they on the trajectory? Okay, we need to know at what x and y they are. We know what time they happened, but remember that time is not shown on our plot of the trajectory. The plot of the trajectory only shows where the particle is, not when. Well, all we have to do is just take our original distance, our original parametric equation, and plug in those values. So for R1, okay, we have our first time, which is just a half a second. Okay, we're going to plug that in. Let me switch to a good color here. We're going to plug that in, essentially, so t squared, this t becomes a half. Okay, so there's my time in my x-coordinate. Here is the time in my y-coordinate. All right, and once we simplify and do the math, it turns out that our first turning point is at 0.5 meters in the x direction. Okay, so 0.5, really 0.542, a little over half. And then in the y direction, so the green, the up down, we have 3 meters. Okay, so this is my x, this is my y. So there's my first turning point. So TP1, right there. Okay, now I can do the same thing with my second turning point, which is 3/2 seconds or 1.5 seconds. So I'm going to plug in my time. I'm going to simplify the x direction and the y direction. So here it looks like at about almost 4. So let me switch colors here. So almost 4 is my x piece. Okay, and then I'm going up 1 meter. Here's my y piece. All right. So if I wanted to draw R1 and R2, I'm just going to draw R2 so I don't get too much stuff on this plot. But essentially our R2 vector here, that's just going to point right here. Okay, so that's R2. And do remember that the velocity vector is tangent to the trajectory. So anytime if we wanted to draw a velocity vector, it would be the tangent line on this plot. Now, last question. Where does the particle experience the most acceleration? Okay, well, we know how to write the acceleration of a parametric equation. We just have to essentially take 2 derivatives of the position, or in this case, take a derivative of the velocity vector, which we have already. All right, so I'm going to take a derivative of the x piece, and that's just going to give me 3, a constant velocity. Now I need to take a derivative of the y component. And because there's a sine function in there, I'm just going to maintain another sine function. So there's my derivative of the x piece, or the y piece, my bad. Now the question is, where is the most acceleration? Okay, so essentially is, where's the magnitude of acceleration in the range here? Okay, so it says, where's the magnitude this should say where is the magnitude in this range at its max. Okay. We want to know in this range from 0 seconds to 2 seconds, where is the acceleration vector, the magnitude, absolutely maxed out. So we can calculate the magnitude of the acceleration vector. We know how to do that because that's essentially just adding in quadrature. It's the x component squared plus the y component squared. That's kicking it old school from like chapter 3 stuff. So we just need to find the magnitude of this vector and where it is the largest. Well, if we write this out in quadrature, you'll notice that, well, 3 is a constant, and this term has a sinusoid. So essentially, acceleration is the largest anywhere where the sine of pi t is also like its largest value. So essentially, I'm going to get rid of this. No, that's fine. That's fine. I'll leave the pi. Yeah. So what values of t at what times are we getting our maximum output of this sine function? When does it get up to 1 or down to -1? The reason -1 is important. So here's our sine function. The reason the -1 is important is because it's squared, okay? So because it's squared in the in quadrature here, we want the absolute value. Okay, so I want to write whoa, that looks like crap. Okay, absolute value needed. And that's just because it's squared up here. So essentially, we want to know when it's 1 or -1 because the squaring will turn the -1 into +1. Well, it turns out that at t equals 1/2 seconds, well, that's when sine is at its max. And if we wait and go around to t equals 1.5 seconds or 3/2 pi, that's when it's going to be -1. But it's squared, so the -1 becomes a positive. All right, so let me get rid of, let me do it this way. There we go. So it turns out that our acceleration, the magnitude is actually going to be here, here. Max acceleration. Okay, and we just did that from determining the magnitude of the vector with the typical quadrature approach. Now, the interesting thing is, we can relate this back to what we started talking about at the beginning with the ball rolling through the valley. So here we have the situation of, in this valley, in this curve, we have an acceleration pointing inward into the curve. But we have the same thing here. We have acceleration pointing in. That's changing the direction. A changes. I'm going to say A changes the direction R. And is inward. Okay, and that happens again here. Notice that this particle is maybe going around something, going under something, and back up. Maybe it's a bird swooping down to the ground and going back up again. Because it's going through that curve, our acceleration is going to point upward into the curve. So just a quick summary. As an object moves, its velocity vector can change in 2 possible ways. You can change the magnitude, so a change in speed. That's an acceleration, or you can change the direction of the velocity. Even though the magnitude does not change, if the direction does, that's also an acceleration. Okay, so there's 2 different ways. Accelerations have a parallel component. Okay, well, the parallel component changes speed. The perpendicular component, well, that changes direction. Okay, and then anytime we have one of these situations where an acceleration is pointing toward the center of a circle, well, that's a centripetal acceleration, and that's the acceleration holding that circular trajectory in shape, so to speak. And then, of course, we have these three equations that we can actually use and model motion with parametric equations. And it's simply just distance. This is distance in 2 dimensions, your velocity in 2 dimensions, and your acceleration in 2 dimensions. So I hope you enjoyed talking about some parametric equations. If you take an upper level dynamics course as a mechanical engineer or an aerospace engineer, or you decide to go into physics, these are things that will pop up when you're talking about the position of objects like satellites in space, like the Voyager spacecraft. You can talk about with parametric equations. Of course, it'll have an x, y, or an I hat, j hat, and k hat component because there's a z component, a vertical component as well. So we'll have 3 dimensions that we can model with parametric equations. So do think about these. You might have one parametric equation to play with on a problem set or a lab. But like I said at the beginning, this is a little more advanced than what you would see in a typical Physics 1 course. But given that a lot of you all are wanting to go on in engineering or the sciences, I think it's good to sort of get a preview of what you're going to see. So as always, if you have any questions, please let me know in Teams or you can send me an email.